Welcome once again to the Zener Diode lecture series. So in part 2 we shall be discussing one application of the Zener Diode as voltage regulator. So those who have not seen our previous video, please go through this overview of Zener Diode. Concept will be little more clear. So here we shall start with the VI characteristics. Now in the VI characteristics, if we have a look, we can easily see that in forward bias, Zener diode will act like just a normal diode. But in reverse bias, we find that breakdown occurs at a lower voltage due to the high impurity concentration, and when breakdown occurs, what we call as Zener voltage, even with the increase in the reverse voltage, there shall not be increase in the voltage across the diode, but current will keep on increasing drastically. So that is the phenomenon, and Zener diode is forced to work in the reverse bias direction. So as a result of that, we can use Zener diode as a voltage regulator. So current will increase but voltage will remain same. Now there are two cases. So case 1 is about the variable input voltage, what we call as line regulation. So line voltage may be variable, and according to the variable line voltage, voltage across the load or voltage across the Zener diode will remain constant. And second case, keeping the line voltage same, if we vary the load, but the voltage drop across the load will remain constant. So we call this situation as load regulation. So let us first see the regulation for variable input voltage, that is line regulation. So consider this circuit where our line voltage, let us consider it as E, which is variable in nature, and the Zener diode is connected through a series resistance, and the current across the total current across the resistance or across the circuit is I, where it is getting divided in two branches. One is IZ, another is IL. So IL is current passing through the RL, and here we have the voltage drop, which is VZ. Now the voltage drop across these 2 points and across these 2 points will be same, so we are naming it as VZ. So we can write that VZ equal to IL into RL. So this is an interesting result, and the current IL flows into the load RL, and the magnitude of IL always remains in such a way that VZ equals to IL into RL. Now this is evident, the load voltage must be same as that of the Zener voltage. So if the supply voltage now increases, more current is drawn from the supply, so I will be more. And since Zener diode is operating in the breakdown region, its current IZ increases, that is increasing, and there is no appreciable voltage drop due to this increase in the current. So since it is working in the reverse bias, and in previous slide we have seen the reverse characteristics. So the result is that the constant voltage VZ is maintained across the terminals and across the load as well. So thus the variation of the supply voltage over a certain range are effectively taken by the Zener voltage regulator. So as a result of that, even if we are varying this line voltage or supply voltage, our load voltage or the output voltage remaining constant. Hence we are calling this as the line regulation. So objective of the Zener diode is to keep the voltage drop across the load same or constant. Now the second case, we call it as the load regulation. So we consider this circuit. So here you see that load is now variable in nature. Now if the supply voltage remains constant but the load resistance keeps changing, even then the voltage across the load should remain unchanged. Now if the load decreases, then more current flows into the load. So quite natural, here the resistance, it will find a lower resistance path, so IL will keep on increasing, and if the load increases, then load current will decrease. Now since the load is in parallel with the Zener diode operating with a constant breakdown voltage, which is Vz, now it is clear that voltage across the load remains constant. Thus, irrespective of the change of the supply voltage or the load resistance, the load voltage always maintaining a constant level, which is Vz. For the Zener diode to operate in the breakdown region, the voltage across the diode must be at least equal to Vz. Now from this figure we can say that E equal to, this is E is, if we consider this particular loop, then we have a drop here and we have a drop here. So we can say that E is equal to I into Rs. So Rs here is the resistance that we put in series plus Vz. So Vz we can write as E minus I into Rs. So let us call it equation number 1. Now if the voltage across the diode is less than Vz, the diode is evidently off and hence it acts as an open circuit. In our previous lecture, in equivalent circuit that we have seen, when Vz is greater than the supply or reverse voltage, then diode acts as an open circuit. Now in such situation, we have the total circuit resistance that is equal to Rs plus RL. Then the circuit current I, that will be equal to E divided by Rs plus RL. So here the load voltage VL, so if we consider this output voltage or load voltage as VL, then we can write VL that is equal to I into RL, considering that this is open circuit. So further we can write as if I into RL, I value we can replace here, I value we can replace from this equation to here. So we can write VL that is equal to E Rs E RL, not Rs, here it is E RL divided by Rs plus RL. So now voltage drop across the resistance Rs, say let us call it V1, then that is equal to I into Rs. So that is what, E into Rs divided by Rs plus RL. So in this way we can write, so we can call this one as equation 2, then VL for this one we can write it as equation 3, this one we can write it as equation 4. So we have also, we can write that E equal to I into Rs plus VL, this thing also you can write. Now if we consider PZ, if we consider PZ as the power rating of the Zener diode, so power rating of Zener diode, Then Pz we can write as Pz is equal to Vz into Iz max. Vz into Iz max. Call it equation number 6. Now if the IL, the load current corresponding to Iz minimum, then total load current I minimum will be equal to IL plus Iz minimum. Similarly, for maximum input voltage or minimum input voltage, E minimum we get Vz plus I minimum into Rs, that is drop across the series resistance plus Vz. So that is what giving us the minimum E. So call it equation number 7, call it equation number 8. So all these equations are helpful to solve or to design a voltage regulator using voltage regulator means load regulator. Here I am talking about load regulator using Zener diode. Now let us try to take an example, things will be little more clear. So in that example we are considering that a 5 volt Zener diode, okay, 5 volt stabilized power supply is required to be produced from 12 volt DC power supply input source. The maximum power rating Pz, so that is given here, Pz of the Zener diode is 2 watt. Now using Zener regulator circuit, calculate the maximum current flowing through the Zener diode, so that is Iz max, then minimum value of the series resistance Rs, load current IL if load resistance is 1 kilo ohm, and Zener current Iz at full load. So this is the circuit. Here power rating is given. So if we try to find the maximum current, so maximum current if we need to find, that is Iz, here what we have to find that okay, so maximum current we have to find, right? So Iz max, so that will be equal to 2 watt divided by 5 volt, that is Pz divided by output voltage, so Vz, that will give us 0.4 ampere or 400 milliampere. So Iz max, that we are getting 400 milliampere. Now Rs value, that we can obtain by Vs minus Vz divided by Iz. Okay, Iz max, because we are finding minimum value, okay, Rs minimum. So Iz max, using this relation, we find that it is 12 minus 5. So this is 12 volt, this is 5 volt. So 12 minus 5, and Iz max we have found 400 milliampere. So that is giving us around 17.5 ohms. So that is the minimum series resistance. Then we have to find the load current IL if load resistor is 1 kilo ohm. So drop across this is Vz, so that is our output voltage also. So Vz is given as 5 volt, and this is 1 kilo ohm, that is 1000 ohms. So that will give us 5 milliampere. So 5 milliampere, and Iz, actual Iz, what we find is at the full load condition, that means 1 kilo ohm load condition. So that will be getting Iz max minus IL. So that will give us 395 milliampere. Okay. So this is how we need to solve. Now I hope you can now understand how to design a voltage regulator using Zener diode concept. So we end here, and let us summarize this lecture. So first of all, when forward bias, the Zener diode behaves like a normal signal diode, but when reverse voltage is applied on it, voltage remains constant for a wide range of currents. Then due to this feature, it is used as a voltage regulator in DC circuit. The primary objective of Zener diode as a voltage regulator is to maintain a constant voltage across the load resistance. And voltage regulation, we have two types. One is line regulation, another is load regulation. So that's it about the Zener diode as voltage regulator. Thank you, and next lecture series will be starting soon. That will be on transistor. Thank you.